Today I will discuss about two more theorems on real numbers. The first theorem was Euclid's division lemma, and the second one was fundamental theorem of arithmetic. Now the third one that I will be discussing is this one. If P is any prime number and A be any positive integer, then if P divides A square, P divides A. This is the definition of the theorem. Now this proof of this theorem will not be required now. This theorem will be used for proving the next fourth theorem. What is the fourth theorem? In NCERT book, the theorem is given as square root of 2 is irrational. Prove that square root of 2 is irrational. Actually, square root of any prime number is irrational. So root 3, root 5, root 7, root 11, all are irrational. So I'll be writing the theorem in general. Instead of root 2 irrational, I'll be writing the theorem as that. Prove that square root of any prime number is irrational. So this is the general definition of the theorem, that is square root of any prime number is irrational. Or let me actually write in this way. This is the theorem, so don't write the proof here. Square root of any prime number is irrational. This is the theorem. So now I'll show you the proof of the theorem. The proof of the theorem will be done by the method of contradiction. So what is the method of contradiction? In method of contradiction, we assume the opposite of the statement what is asked to prove. So here we have to prove that square root of any prime number is irrational. So we'll assume the opposite of that. So let the square root of any prime number is rational. Or actually we write, let us assume to the contrary. Let us assume to the contrary. That the square root of any prime number is rational. So that is we are assuming the opposite of what is asked to prove. In the method of contradiction, we always start with this assumption, the opposite thing. So let P be the prime number, P be any prime number. So what we have assumed, the square root of the prime number is rational. So therefore root P is rational. So rational, you know, any rational number can be expressed in the form of P upon Q. That is therefore we can write root P as in this form, where A and B where A and B are co-prime positive integers. That means co-prime positive integer means that A and B, they don't have any common factor. That is the meaning. Co-prime, you know, they don't have any common factor other than 1. And also b cannot be equal to 0 because division by 0 is not defined. So these two things are in our assumption. That is, when I define that p is root p is irrational, that means root p can be written in this form, where these two are integers, co-prime integers. Actually, they are in the lowest form. That's why it is written co-prime, because any rational number is, let's say 4 by say 6. This is a rational number, ratio to integers. But the lowest form, what is the lowest form? You cancel. This is the lowest form. So when the rational number is in their lowest form, then the numerator and denominator are co-prime. You see, 2 and 3 have no common factor. So this is in the lowest form. So that's why a and b are co-prime positive integers and b cannot be 0. So that's why this is the assumption we have made. Okay, now, so you see, so this is okay. So now let us square both the sides, then it will become p. So it will a square by b square. So cross multiply, then a square is equal to p into b square. So you see, in this, p is a factor of a square. That means p divides a square. And p is a prime number we have taken. So by this theorem, that is, if p is prime number, if p divides a square, p divides a. So using this theorem, I can say, right, since p divides a square, therefore p divides a. So this is our statement A, statement E, or statement 1 also I can write. So it's simple, squared. I have squared the thing, cross multiplied, and from this, by observation, I see, since p is a factor of a square, that means p divides a square. Therefore, by this theorem, p divides a. So this theorem is used here. Then, okay. So since p divides a, therefore p can be written in this way. P divides a. Okay. Okay. No, that means a is a factor. P is a factor of a. So a can be written in this way. P into some integer. Because p is a factor of a, so I can write a in this way, where m is any integer. M is any integer. Now what I'll be doing, this value of a is pm, I'll be like equation 1, say. So I'll be using this value of a in equation 1. So this will be a square will become p square n square. Equation 1 will become, in place of a I am writing pm. So a square is p square, m square is equal to p into b square. So this being written in this way. So this p getting cancelled, or p into m square is equal to b square. I get this. So here again p is a factor of b square. That means p divides b square. So by this theorem, since p divides b square, so p will divide b. So by the above, therefore by above theorem, p divides b. So you see, starting with the assumption that is root p is rational, and then with the definition of a rational number and with some algebraic process, we are getting two conclusions. One, first a conclusion, p divides a, and the other conclusion, p divides b. So what does it mean, a and b? That p is a common factor of both a and b. So from a and b, what do we find? That p is a common factor. P is a common factor of both a and b. A and b. From these two, we come to the conclusion that p is a common factor of a and b. Now, what was the assumption that A, B are co-prime? So there is a contradiction. Our assumption was A, B co-prime, but we are finding that with this assumption we are coming to the contradiction that A and B have a common factor P. So this contradicts our assumption that A and B are co-prime. So we come to a contradiction. So that means what? So this contradiction arises due to a wrong assumption. What was our assumption? That is root P is irrational. So this is wrong because of the contradiction. So this assumption is wrong. That means root P is not rational. Therefore root P is irrational. Hence proved. So in this way logical explanation, this is known as the method of contradiction. This proof is done by the method of contradiction. Method of contradiction. Okay. So I think this is clear. That means again when you have to prove this theorem by the method of contradiction, we assume the opposite of what is asked to prove. So we write, let us assume to the contrary that the square root of any prime number is rational. So if P is prime number, then this is rational. This is our assumption. So I can write in this form where A, B are co-prime, B not 0. Then by squaring and we can come to this that P is a P divides A. That means P is a factor of A, and then putting this value of A is equal to Pm in this equation 1, we find that P is also a factor of B. So this contradicts our assumption. So we assume, so we come to the conclusion that our assumption is wrong. So this is the method of proving this theorem, that square root of any prime number is irrational. So actually, if now you take P is equal to, first you P to 2, that means in that case you have to prove that root 2 is irrational. So you will assume root 2 is rational. So in place of P will be always be 2. You have 2 divides A and you will get 2 divides B. So you write 2 is a common factor of both A and B. Hence contradiction. Then if I have to write root, when I take P to be 3, then root 3 will be irrational. We have to prove. So in that case, this will be, this in place of P will be writing 3. 3 divides A and here 3 divides B. So 3 will be the common factor. So actually you see, square root of a prime number is irrational, and you will be finding that the prime number whose square root you have to prove to be irrational will be the common factor of both A and B. So in this way we prove. Okay. So now let us solve some question. So here you see, you have to prove that 5 plus 3 root 2 is irrational. So again, this kind of question or this kind of proof will be doing by the method of contradiction. So we'll assume the opposite. Let 5 plus, or let us assume, always let me write in this way. Let us assume to the contrary, that 5 plus 3 root 2 is rational. So this is the first step. We assume the opposite of what is asked to prove. So this is rational, we have assumed. So we can write this number, since this is rational number, so I can write this in the form P upon Q or A upon B, whatever, A upon B let me write. That is the rational number in its lowest form. That means A and B are co-prime positive integers and B is not equal to 0. So always we write these things. Whenever I express this in the form a by b, that means this is in the lowest form. So a and b, the numerator and denominator, are co-prime. They don't have any common factor other than 1. And the denominator cannot be 0 as division by 0 is not defined. So what we'll be doing here, you see, now there is a square root. I know square root of any prime number is irrational. 2 is a prime number, so root 2 will be irrational. That I can prove. I have shown you the method of contradiction. So what we'll be doing, 5 is a rational number, so I'll transpose this rational number to the other side. So 3 root 2 is equal to a upon b minus 5. 3 root 2, now simplify, b is the LCM, a minus 5b. Okay, and next step, we keep root 2 in the left hand side, so it will be a minus 5b upon 3b. So this much simplification we have to do, so that I keep the square root of the prime number in the one side and the remaining terms on the other side. Now our logical reasoning will start. You see, the left hand side is irrational. Left hand side is irrational. It is proved. And look at the RHS. RHS, you see, a is an integer and b is another integer. So 5b is another integer, and difference of two integer is another integer. So a minus 5b is an integer. So the numerator is an integer, and the denominator 3 times an integer is again another integer. So it is the ratio of two integer. So ratio of two integer is a rational number. So RHS is rational, since a 5b, a minus 5b and 3b are all integers. That is the meaning. This is an integer, this is an integer, this is an integer, and difference between these two is also an integer. So the ratio of two integer is a rational number. So what I see, the LHS is irrational, that we have proved by in the last class, and RHS is rational, the reasoning I have shown you. So how can it be possible? Is again a contradiction. It cannot be an equation. It cannot be like that. The one side is irrational, other side is rational. It's not possible. So it's a contradiction. So this contradiction arises due to our wrong assumption. So our assumption is wrong. That means, therefore 5 plus 3 root 2 is irrational. Hence proved. This is the reasoning. So we always we assume the opposite one what is asked to prove. Then we proceed, do some algebraic simplification, and then we come to some contradiction. Then we conclude that the contradiction is only due to a wrong assumption. So our assumption is wrong. This is wrong assumption. Hence, it cannot be rational, so it has to be irrational. Hence proof. So in this way, we can prove this kind of questions. Okay, that's all.